Welcome to another iteration of Psych 462, and today we're going to discuss stimulus control. And I can tell you are so psyched for this. Yes, I can. All right, let's see if we can figure out where this went so that we can share. I know it's around here somewhere. Yes, I do. Where's my entire screen in my application window? And here we go. Oh boy, stimulus control. So, what do we need to know about stimulus control and why? Well, stimulus control is having stimulus control means that the probability of the behavior varies depending upon the stimuli that are presented to the organism. If behavior is under stimulus control, then the behavior happens when the S plus, the stimulus, is present, and the behavior doesn't happen when that particular stimulus is absent. So most of our behavior is actually under stimulus control. A person that contributes to a charity generously while in church may watch every penny spent while at work. So you can be a hoarder in one situation, not give up things, and give up things in a different situation. A dog should sit when you say sit or when you hold a treat. It doesn't say sit when it's running after the ball. So our behavior is going to change depending upon the context. And remember, the context is full of all sorts of S pluses, of cues. And we're going to vary our behavior depending upon stimulus control. And in order to teach stimulus control, it's going to involve teaching discrimination to the cue. So what we're going to look at, and this is a classical conditioning example, is every time a particular cue, say a red triangle, is presented, the animal responds more and more. And of course, on the first couple of trials, it's not responding, and it's going to continue its responding to the S plus, in this case, our red triangle. But it's going to stop responding when it comes to a S minus. So maybe we show a green triangle. So in the presence of the S triangle, something, or the red triangle, something's going to happen. And in the presence of the other triangle, it doesn't. And so you begin to focus on the stimulus that is predictive. In operant conditioning, you'd focus on the stimulus and required behavior that gets you the treat. So when I say the word sit, the dog doesn't know English, but it's learned that sit means if I put my butt on the ground, I get a treat. And so the dog sits. Again, I could teach that dog any word to cue the sitting behavior. It doesn't matter, but as long as I use it consistently, the dog will learn to discriminate to the word sit or whatever word I choose to use and then sit. So stimulus control involves discrimination, and discrimination is the degree to which the antecedent stimuli set the occasion for particular responses in operant conditioning. It's the precise degree of stimulus controlled responding. How much responding is controlled by the stimulus? So we might want to understand who daddy is. So a man has a beard and is daddy. So daddy has a beard. A man also has a beard, but he's Uncle Eddie. And the child should only call daddy daddy. He should not call Uncle Eddie daddy. So we learn to discriminate. And stimulus discrimination is taught by using discrimination training procedures, such as differential reinforcement. And in differential reinforcement, obviously responding, we're only going to reinforce particular stimuli, hence the term differential reinforcement. We respond only to the target. We reinforce only if the animal responds to the target behavior in the presence of a particular stimulus, and we don't reinforce if it doesn't. We also have to worry about stimulus control and generalization, because it's nice that you learn to stop at the red lights in your town, but it would also be nice if you learned to stop at the red lights in other towns. And so a stimulus generalization is when a response is reinforced in the presence of one stimulus. There is a general tendency to respond in the presence of new stimuli that have similar physical properties or have been associated with the stimulus. So it's a loose degree of stimulus control. Okay? And this can be problematic. It can be very nice if you stop at red lights anywhere you go, but it can be problematic if a baby calls all men with beards daddy. Okay? Then the baby has not formed discrimination. The baby is generalizing that daddy is anyone who has a beard, and now they call daddy anyone who has a beard in the grocery store, and this can be highly embarrassing. But we're also going to teach stimulus generalization by using generalization training procedures. And with these procedures, one reinforces any stimulus within a class of related stimuli. So maybe we want you to understand men, and we reinforce anyone who meets that criteria of a man. But we don't want somebody to be reinforced for calling a woman a man. And so we have to teach one to discriminate and one to generalize, which makes stimulus control quite difficult. So how do we develop stimulus control? Well, stimulus discrimination training requires a certain behavior and two antecedent stimulus conditions, the SD and the S delta. And the SD is the S plus, the S delta is the S minus, and I find it much easier to call them S plus and S minus. But we want responses that occur in the presence of the FD to be reinforced. So thus the response increases in the presence of the SD or the S plus. And responses that occur in the presence of the S delta or S minus are not reinforced. The response decreases in the presence of the S minus. So we reinforce the child saying red when someone asks, what's your favorite color? But we withhold reinforcement if they said red when we ask, what's your name? Unless, of course, their name actually is red. And then we don't use that. So what's your favorite color? And the child says red. Super, you said red. But if I ask, what's your name? And you say red, you don't get any praise and you're ignored because that would be an incorrect discrimination. Red means a color in this case, not your name. So we're going to involve some differential responding. We're going to have to shape that responding. So when an organism's behavior comes under the control of the SD or S plus has acquired stimulus control over the organism's behavior. So the verbal stimulus, what's your favorite color, gains stimulus control over the response red, or whatever the child's favorite color seems to be. Why does that occur? It's because the organism is discriminating or responding differentially, is what we would say. Stimulus generalization occurs when a response is reinforced in the presence of one stimulus as well as similar stimuli. That is, the same behavior response tends to be evoked by stimuli that share similar physical properties with that controlling antecedent stimulus. Stimulus generalization is more likely when the stimuli are highly similar to the original stimulus that was presented. So you stop at the first traffic light you come upon in driver's ed, but you generalize your responding, so you stop at any red traffic light in any city or town. But notice you're not stopping at yellow or green, although maybe we should shape stopping at yellow. But you know that yellow and green don't mean stop, red means stop. All right? So if I'm teaching green and I present a colored circle, let's see if it'll go back. All right, so I have green. The student's most likely to say green. But when are they most likely to say green? They're less likely to say green to certain stimuli, and they're more likely to say green to other stimuli. So I would argue that these stimuli you'd likely to say green, maybe this one, but definitely not these three, and definitely not these three. So we would say green to these types of stimuli. And if this one was my original S plus, this is close to that S plus, this is close to that S plus, and I probably not get as many green responses to this one or to this one as I would to this one, this one, this one. And again, this is a good example of testing color vision. What does the animal see as green? So in stimulus generalization, we're going to do the opposite. We respond to similar stimuli to the original stimulus. So that could be similar people, materials, settings, and so on. And generalization is more likely when the novel stimulus is similar to the training stimulus. So I can do stimulus discrimination and stimulus generalization. And generally, as the training and test stimuli become more different, responding will decline. And this produces a generalization gradient. So here I've got an S plus. And what we see is that this is actually light in nanometers. If 580 is the yes, we get 590, 570 gets a fair amount of responding to it. But as I get farther away from that wavelength, the animals reduce their responding. So here we have a pretty good discrimination gradient. Now I could also get a generalization gradient, which would be more flat, where the animal is responding more. And I think if you look at this, you'd say, well, that's pretty flat in comparison to this responding and this responding. So I can tell what the animal seems to say is a yes and what the animal seems to say to no. Again, here's another generalization gradient from Gutman and Kalish in 1956. Again, in the wavelengths, the original S plus is 590, right? 580 is pretty good. 600 is pretty good. But pigeons were reinforced for pecking an orange-yellow light on a VI schedule. And then the generalization test is when I present many different colors. And we find that they peck at colors that are highly similar to the original S plus and less so to the ones that are farther away and less orange-yellow. Here we get an S. Here was our original S plus. The animal couldn't tell the difference here. Here, when we look at brightness of a light, we can train the animal to look at how bright the light is. And of course, we get the S minus as a dim light. And we know that the animal produces a nice gradient here where it says, yes, I recognize what the S plus is. And if I've only trained to brightness, I can test wavelength, and I should not get a discrimination gradient because I didn't teach that. But I should get a brightness gradient if that's the target that I was looking at. See how that would mean? This would be, okay, yes, I get the idea of bright versus dim. I've never been taught differences in colors. I should just get a very flat generalization gradient. I should not get any kind of discrimination gradient. All right, we can get excitatory gradients where I get increases in responding. I also get inhibitory gradients the same way. So maybe I teach 500 is the CS minus and 800 is the CS plus. I should see as things get farther away from 500, then I get an actual decrease. As I get closer to 800, I begin to get more responding. And as I get farther away, I get a little bit more responding. And so we can teach an S plus, we can teach an S minus. And the interesting thing is what happens when I put these two together. Then we get some interesting things. In fact, what I get is peak shift. And peak shift is where the peak shifts away from the S plus. Okay, so it's not at the S plus anymore, but importantly, it shifts away from the S minus. So peak shift always is a peak shift away from the S plus in the direction of away from the S minus. And so it's a phenomenon where the peak of the generalization curve shifts away from the S minus. And it means that the most responding doesn't occur for the S plus, but it's slightly offset from the S plus and away from the S minus. The peak of responding shifts away from the S minus. And the question is always, of course, why? Here's another example of peak shift. And what we see is here's the original training, and we see the most responding occurs here, and there's no peak shift. But now if I add an S minus, so I have, this is a yes, and this is a no in this case, okay? And here's my no, the peak begins to shift away from the no, even though this still remains yes. I still get a lot of responding to the yes, but because now I've added this is a yes, this is a no discrimination, in this case, the peak shifts here. I add a different no. Ooh, now my no is very close to my S plus. Now, the top responding occurs here, top responding occurs here, but also it shifts away. The second most responding is even farther away from that S plus and is more towards the S minus. But even my S plus is shifted away. See how it shifts away? The most responding shifts away from the S plus as well. Okay, got it? And it's not going to give me anything. Okay, so let's go ahead and go oh, here we go. And here I'm going to have a third one. Okay, see how we go? Why does this occur? Why might this occur? And the answer seems to be two reasons. And it depends on whether you believe in Spence or you believe in Curler. So Spence's theory is that the peak shift occurs because of the summation of the excitatory and inhibitory curves. So the result is that most responding is slightly in favor of the S plus. It's not, you don't get as much suppression for the S minus, but you get enough that when we add the two curves together, the sum of the two shifts the responding away from the S plus, and it's just a math phenomenon. So here is our excitatory, here's our inhibitory, and if we were add these together, the most responding occurs, so we have to add this kind of minus this, and that ends up with the most responding being slightly away from the S minus. And so here's our S minus. Our peak is going to occur slightly away when we add these together. All right, here's our S plus, here's our S minus, and the peak is the summation of the two, and what we should get is the peak will shift over here when I do yes and no situations. Now Curler says, no. That's not it's not a math problem, it's an interdimensional problem. And what you have is a transpositional interdimensional theory. The animal is learning a concept rule. When given a stimuli, given two stimuli, you choose whichever fit the characteristics of the original S plus to S minus. So you choose, if the original S plus was big and the S minus was smaller, you learn to always choose larger. If you learn that the original S plus was green and the original S minus was red, you choose the most green and the least red. So when given a generalization stimuli, you look for whatever is the most S plus compared to what would be the S minus. And so you learn this transpositional rule. I'll give you some examples of these and you'll say, oh yeah, I see what's happening. So Curler's model says you shift away from the S plus because the organism compensates for not S minus and overcompensates for the past S plus away from S minus behavior. So they're learning a concept. Always choose larger, always choose greener. So given a large and small stimulus, you choose large even if it's too large. If the original stimulus is red and the S minus is green, you choose the reddest and least green. So the animal is learning a concept rule, not the S minus, but the S plus. And yes, that's a rule, not the S minus, but the S plus. So when given a generalization stimuli, you take whatever is the most not S minus. And you the shift away from the S plus occurs because of this choice rule. And you'll see how this happens in just a second. So let's set up a test of the theories. And so our original training is going to be 100 centimeter squared circle, or square, 100 centimeter square versus a 50 centimeter squared square. All right, so we have 100 square and a 50 square. And the original yes is the 100. All right, 100 is yes, 50 is no. So now I give a 250 and 150 test. Spence would say you would choose the 150 because it's closest to the original S plus. On test 2, when we give a 500 centimeter square or 250 centimeter square, Curler says you would choose 500 over 250 because 500 is bigger than 250 and our original stimuli was 100 minus 50. So Spence would say, oh, no, you still go for the 250. Okay. And which is right? Spence says you choose closest to the original S plus. Curler says you'll choose whatever is the larger in this test situation. And what do the animals do? Well, the tests for summation yield evidence supporting Spence's theory. When the stimulus is close to the original stimulus, and the animal tends to make errors towards the original stimulus. But when you get farther away from the original stimulus, you get too far away from the original stimulus that the animal can no longer, in a sense, remember the original stimulus, then tests for transpositional interdimensional yield evidence supporting Curler's theory, that when the stimulus is highly different from the original stimulus, the error is towards the original stimulus, and that you show a concept rule, you keep the relationship of the difference constant. So if the rule was choose larger, you choose larger. If the rule was choose smaller, you choose smaller. If the rule was choose red, you choose the reddest, and so on. So which theory is right? Both. When the test includes stimuli close to the original S+, the animal chooses the one closest to the S+, supporting Spence. As the differences become increasingly larger, the animals tend to choose the stimulus consistent with the type of difference between the S+ and the SR. So you choose the larger or the redder. Why? We're not exactly sure. But we think it has to do with the ability of the animal to tell the relationship between the two stimuli versus choosing the exact stimulus versus choosing the relationship between the two stimuli. And as we get farther away from the original stimulus, the animal can't remember the original stimulus, and thus he chooses the relationship instead. Now, we have to sometimes teach the stimulus discriminations. And you all learned this when you learned your letters. You had to learn that an A was not a B. And we know that you're going to have more difficulty when you have letters that are similar looking, like P's and Q's. Under the lowercase p's and q's and b's and d's are hard for children to discriminate. But discrimination allows us to differentiate when reinforcement is available for specific responses. So if I show you a B, I want you to say B, not D or P or Q. Okay? That would be the correct response. And many essential tasks require these discrimination skills, certainly reading, labeling objects, following directions. You have to know what I mean by that direction and able to do it. Following activity schedules, greeting people, you need to make sure they're the right person. And even self-care skills require discrimination. You have to know what is the deodorant and what's the toothpaste, right? It's an important discrimination. So the basic problem of discrimination training is that discrimination training teaches learners to perform a specific response in the presence of a specific stimulus, and not to perform that response in the presence of other stimuli. But most stimuli are compound. They consist of different elements. So a stimulus isn't a clear, it's not like we can do red versus green. Even with red versus green, we have to present them as a shape of some kind, right? You can't just have red over the whole page, because even the page has a shape. So it may be difficult to control which elements of the stimulus exert control over the behavior. What is the organism attending to? So we must be careful how we teach and what stimuli we use. And again, all stimuli are compounds. They consist of many different elements. The modality may differ, visual, auditory, tactile. They may differ in size, color, shape, and so on. And it's difficult, again, to control which elements exert control over the behavior. So we have to be careful how we teach these and what we use as an S+ versus S-. So we can have two types of discriminations generally. We can have simple discriminations that are not conditional. They're simply A equals B. And we can have conditional discriminations, such as matching to sample, arbitrary discriminations, or they can involve other complex conditional associations. We can go through some of these, and you're very familiar with these, but probably not from an operant conditioning point of view. So a simple discrimination is the stimulus present or not. If it's red, then it's an apple. We know that there are many other reasons why it might be red, but we can simply say if it's red, then it's an apple. And an easy way to say it is that's a cat. If it's a cat, say cat. If it's a dog, say dog. We present a single picture, and the only answer for what kind of animal this is, it's a cat. Right? If we cue a dog to sit, sitting is the only correct response to the cue sit. But of course, this isn't real life for most human tasks or for dog tasks either. It's very rare that we get such a simple discrimination. Instead, we get conditional discriminations. And this is where a response to a given stimulus is followed by a reinforcer if and only if another stimulus is present. Or said another way, a stimulus is discriminative for reinforcement or no reinforcement, depending on or conditional on the presence of another particular antecedent. So we often teach this via matching to sample or MTS procedures. If it's a picture of a dog, then say dog. If it's a picture of a cat, then say cat. We vary the answer for the same reinforcement depending upon the conditional cue. So we're going to present a dog or a cat, and I might point to one of those pictures and say, what is this? And then you have to answer me. So many programs consist of identity matching, which is a form of matching to sample. So I could have presenting objects and pictures. I could present letters and shapes, colors and numbers. And so let's get an example of a match to sample. So the learner learns that this is blue. Okay, that's blue. And then I'm going to say, show me blue. And I present 3 different colors in identical boxes. And hopefully the learner will say, this one is blue, not the green or the pink. And I can present this where I show this, and then this array is also presented while this stays. Or I could show this, take away the exemplar, and the organism or the child or whomever has to remember the original stimulus and then pick blue. So if I matched a sample, I can say, here are 3 pictures. Match my picture. And hopefully you'll be able to match. Okay? To show you 3 pictures again, now I show you baby, and that's my sample or conditional stimulus, and hopefully you'd pick then the baby. You wouldn't still pick the flower, right? So now I can teach you different names of things, and then I can conditionally ask you, show me the match. And we can also establish new forms of conditional control. So I can do identity matching with a single mode, visual to visual, auditory to auditory, and I can do arbitrary matching, which is multimodal, visual to auditory, auditory to visual, auditory to tactile. So let's take a look at some arbitrary matching, where the stimuli are not physically identical. In fact, they could be different modalities or different types of stimuli, a story problem or a number answer. Let's get an example. I'm going to match a non-identical visual stimuli, an object to a picture, a printed word to a picture, or an object to a printed word. Or I can match the auditory stimulus to the visual stimulus. Can you think of other examples like that? How could they differ? Let's take a look at this. Here, I show you my 3 pictures again, and now I say, show me flower, and you should point to the flower. Again, I show you 3 pictures, and I say, show me the baby, and you have to point to the baby. Or I could just put the word flower, and you now match it, or the word baby, and you match it. Notice that just putting the word doesn't mean you have to read, it just has to match this configuration. This visual configuration means flower. This visual configuration means baby. So, and I can start to get complex stimulus control. I can get generalization within a class of stimuli and discrimination between classes of stimuli. And I can have 2 procedures for teaching this concept formation. I can use simultaneous discrimination, where I have concurrent presentation of multiple stimuli, or I can have successive discrimination, where I successively present the multiple stimuli. And this is teaching the elements of a stimulus class. So a stimulus class is a set of stimuli that have a common effect on behavior. So red lights all over town would be the stimulus class of red lights, and they should evoke the same stimulus response of stopping. So here we have a circle that says red. And here, this is definitely not red, and these are definitely not red. And so we could probably say that these 3 circles here, most people would respond as red, and the others not red. And so I can use stimulus equivalence. Stimulus equivalence is the emergence of accurate responding to untrained and non-reinforced stimulus-stimulus relations following the reinforcement of responses to some stimulus-stimulus relations. And this has 3 aspects: reflexivity, symmetry, and transitivity. So now my stimuli are going to differ in a little bit different ways. I have a picture of a dog. I have the word dog in uppercase, and maybe I'll say dog. Okay, so we'll say dog. When it's in the quotes, I'm saying dog. And so now if I show you the picture, you should be able to point to the word. If I show you the word, you should point to the picture. If I show you the picture, you should be able to say dog. If I say dog, you should be able to point to the picture of the word dog. If I show you the picture, you should be able to say dog. If I say, what is this? You say dog. And if I say dog, you should show me the picture of the dog. So now we have transitivity here, where all of these stimuli go back and forth and are considered equivalent. So now I have 3 different stimuli that evoke the concept of dog. Okay, A, B, and C, 3 stimuli that are transitive in this respect. So reflexivity is in the absence of training, the person selects an identical stimulus. Logic is A equals A. So example, without specific training, the person matches. Okay, so I've never taught dog, but I've taught lots of samples of when I show you the picture, point to its match. And you spontaneously can do a new one. I show you this picture you've never seen before. And because I've done lots of training of matching to sample, you can match this sample without training. Symmetry. After being taught to match A to B, the person can match B to A without training. And the logic is A equals B, then B equals A. For example, after being taught to match the picture of the dog to the word dog, the person can match the word dog to the picture of the dog. So they can go back and forth. And they know that dog means dog and dog means dog. Transitivity, and this is the critical test for stimulus equivalence, is if the stimuli are members of an equivalence class, you will accept all 3 stimulus. So after being taught to match A to B and B to C, the person can match A to C without training. And the logic is if A equals B and B equals C, then A equals C. For example, after being taught to match, let's get all these in here, dog to dog, and dog to dog, you can match dog to dog. So it goes back to our 3 circle. You can be shown the picture and find the word. I can say the word and you can find the word. And I can say the word and you can find the picture of the dog. And so now I can say it, I can see the word, and I can see the picture, and they all are stimulus equivalent. And now I've got transitivity, and I've probably got pretty good stimulus equivalence and stimulus discrimination here. But notice you're not calling it a cat. You're calling it what it is, dog. Several factors affect how well I develop the stimulus control. One is reinforcement. Am I reinforcing the right behaviors? And typically we use differential reinforcement with very rich schedules of reinforcement. So I'm only going to reinforce correct responses, not incorrect responses to the stimuli. And I'm going to respond highly. When I'm first teaching discrimination, I'm going to reinforce every correct response like crazy. And eventually I can fade it, but initially the rate of reinforcement is very critical. How are they pre-intending skills? Can the subject pay attention? If the subject can't pay attention, I'm not going to teach stimulus control very easily. Right? What type of instruction or materials am I using? Are they easily discriminable? Are they interesting to the person or the animal? If they're not interesting, my organism is not going to pay attention. How specific are my directions? Okay. Have I given clear directions, clear discriminations? If I have, then stimulus control should occur quickly. If I say touch the correct response, say the correct word, so that if it's related behaviors like in a reading task, it'll work very well. But if I say stand up when you see the word dog, I'm likely to get more errors because standing up is not a typical response for seeing the word dog. Saying the word dog would be a more appropriate response. Do you have the opportunity to respond? Am I giving you frequent active opportunities to respond? And if I'm giving you lots and lots of opportunities to respond, I'm more likely to develop stimulus control. And am I pacing the response opportunities? Am I teaching criteria to A equals A before moving on to A equals B? So I make sure that at each step of the way, I'm pacing my response opportunities correctly and not losing your attention, but ensuring that you have the task down. You've learned each task at each step of the way. I'm much more likely to get good stimulus control. And then, of course, the salience of the stimuli. Are they worth paying attention to? Can I tell the difference between them? Or are they so close that I can't tell the difference? And this is dependent on the capabilities of the individual, the past history of reinforcement, and the particular situation. Color discrimination is going to be more difficult to do in low light. Somebody who's deaf is not going to do very well if I'm using a lot of auditory discriminations. So, and the more modalities I use in presenting the stimuli, typically the better the concept is learned better. And think about it, if I see it and I say it and I do it, I'm more likely to remember it because I've now got stimulus control in 3 different modalities. Other factors, well, masking and overshadowing. Masking is what we might call blocking. They call it masking in the discrimination control world. Overshadowing. One stimulus is so interesting, they don't pay attention to the other. And I can get over these by making changes to the physical environment, making better instructional stimuli that are intense and centrally located, and I can reinforce behavior in the presence of the relevant stimuli and not accidentally reinforce in the presence of the non-relevant stimuli, which sometimes can be hard to do. But what we look for, and when we know stimulus control has actually occurred, is the behavior occurs immediately upon presentation of the stimulus cue. The behavior never occurs in the absence of the stimulus cue. The behavior never occurs in response to another stimulus, and no other behavior occurs in response to the stimulus. So you say dog when you see the word or the picture of a dog. You never say dog in the absence of a dog. You don't respond with dog to another stimulus picture of, say, a cat, and you don't call the picture of the dog cat. So we get the response dog only in the presence of the stimulus that mean dog. And how can we do this? Well, one thing we can do is use errorless learning. And then we also have to remember when we're presenting stimuli, something called the feature positive and feature negative effect. All right, let's talk about errorless learning first. And this was developed by Herb Terrace, who did a lot of chimp language stuff later on, but he's actually most famous for his errorless learning. And we use it when teaching a cue, and we use multiple cues and multiple responses. And I want to start with one cue meaning yes, the second cue meaning no. And I only establish other cues when I'm sure that I've got the first cues down pat, the animal actually uses them. And I'm going to take appropriate responses for only that cue and that behavior, and I'm going to keep them separate. So when I use the word down, I want to make sure that I've clarified, does down mean stop jumping on me or lie down on the ground? Because I can't use them interchangeably or my animal is not going to learn down. I have to make sure that I'm only using down as having one meaning and one meaning only. My prompts are going to be important. Prompts are used to increase the probability that the organism will engage in the correct response. And I use these in discrimination training. So my SD or my S plus means do it. My S delta or my S minus means don't do it. And the function of the prompts is to produce an instance of correct behavior so it can be reinforced. And I can have several different kinds of prompts. I could have a verbal prompt. What do you see? I can have a gestural prompt. I can point to the stimulus. I can model a prompt so I can observe my organism that I'm trying to teach observes me doing it, then they imitate it. And I can have physical prompts where I physically assist the rat or the child or the dog to engage in the behavior. Physical prompts, I think, are more used actually in humans. Modeling prompts, depending on the level of the organism, and gesture and verbal prompts as well. So what types of stimulus prompts can I use? I also have stimulus prompts that are within the stimulus. So I can change the stimulus to make it bigger or soft or smaller in a visual prompt, make it louder or softer in an auditory prompt, and make it more or less, say in a color saturation prompt. Or I can have extra stimulus prompts where adding a stimulus increases the likelihood of a correct discrimination. So I can have a picture next to the word. Or I can have a line of food pellets for the rat to follow or the child or the dog to follow. So they follow the trail so they know where to go. So maybe they have to go down a path. All right. Does that make sense? I can teach behavior chains. Maybe my stimulus requires several behaviors in it. So one behavior becomes a cue for the next response, and this becomes a behavior chain. So maybe the dog has to run through the tunnel, over the balance beam, and then through the weave pools. So I can teach this forward. I start with the tunnel, and then the dog goes over the balance beam after it does the tunnel. And when it can do the tunnel fluently, I add the balance beam. When it can do tunnel, balance beam fluently, I add the weave poles. And I teach each in succession, and I teach them to criterion. Or the backwards chain where I start with the weave poles, and then I move to the balance beam followed by the weave poles, and then I add the tunnel to the balance beam to the weave poles. And actually, it turns out backwards chains work best. If I start with the behavior closest to the reinforcer and move back, I tend to get more stimulus control, and the animals seem to get it faster. Because now one behavior really does become the cue for the next one, which cues the reinforcer. I also need to fade my prompts. I can't walk around going, "What is that?" or "say thank you" all the time. So I need to transfer stimulus control into the organism. So I'm going to have to fade my prompts, or I'm going to have to teach the organism to use prompts in their natural environment. And I may have to delay the prompt. I may wait until the organism makes an attempt and increase the delay before the prompt would have been given to give my organism a chance to make the response on themselves, for themselves. So let's go back to Herb Terrace and think about how we can use this to teach errorless discrimination. And Herb rightfully criticized the way most discrimination learning or training was conducted, in that the subjects are allowed to make many, many errors. And when the subjects get frustrated, we also see a lot of aggressive behaviors because they're frustrated because they can't figure out what's the right response. So he suggested, how about we use errorless learning instead? Here, the subjects are allowed to make very few or no responses to the S minus. And it differs from a traditional response in two ways. Rather than waiting for a steady response to the S plus, it introduces the S minus early in training, and it has a distinct fading procedure that's used to make it unlikely that the subjects will respond to the S minus. So if I'm going to teach the S plus is red, the S minus is green, when I'm teaching red versus green discrimination, I present the S minus for only about 5 seconds, but the S plus for 3 minutes. The pigeon pecks for 3 minutes on the S plus, and then the S minus pops in for 5 seconds and is taken away. And it's taken away so that they learn red is the S plus. And then I can also begin to gradually fade to green and then back to red. So the animal learns green versus red. No responses for green, more responses for red. And I can show you this in terms of teaching a human being. And it makes much more sense when I describe a human being's behavior. So maybe I want to teach children with cognitive disabilities sight words. And there are actually sight words that from the DOLT sight word list, things like police, exit, safe, crosswalk, walk versus don't walk. We want to teach these children. And they are important words in their environment. But let's say I want to teach the child rat. And so I'd start with this slide that has both the picture of the rat and the word rat on it. And I ask the child, "What is this?" And the child says, "Rat." Good. But now I've got two cues here, one of the picture and one of the word. So now I change the background, but I make the foreground of the word more obvious. Rat. What is this? Rat. What is this? Rat. What is this? Rat. What is this? Rat. 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 And so I faded the background picture slowly over time, leaving just the word. And so the child responds rat, because he slowly learned to pay attention to the word. By fading the other properties here, he's learned to attend to the word and not to the picture. And so he learns the word rat. And this tends to be a very good way to teach, particularly for organisms that have trouble with stimulus discrimination. And we know that children with severe cognitive disabilities tend to have more difficulty forming these discriminations than other children. Kids with autism have a horrible time forming discrimination and generalization. So we use errorless learning because it reduces the number of responses to the S minus. It improves long-term discrimination. And Terrace's work shows that you don't get the aggressive responses that with the fading procedures that you do if you just introduce them naturally. And interestingly, using errorless discrimination eliminates peak shift. And you don't get behavioral contrast as well. So you can avoid these problems by using errorless learning whenever possible. We do, when we're using feature positive effects, have to make sure we use errorless learning or teaching any kind of discrimination after. Watch out for something called the feature positive effect, because there are some limitations on the effectiveness of discrimination training. And again, discrimination training can't occur if the animal can't detect the difference between the stimuli. And the animal won't form the discrimination if they're not properly attending. And how do they not properly attend? Well, not only are there differences within an animal, but there are all species differences. And for those species differences, what is a salient stimulus differs across species, and their past learning history and just their biology can make a difference for what they learn and how well they can learn it. So there's a classic experiment that shows the feature positive effect, and this was by Hurst and Jenkins. Actually, Jenkins and Hurst was a publication. Pigeons were given two stimuli simultaneously, and they had the dot, meaning the S plus, and no dot was the S minus. So the pigeons pecked the S plus, they got reinforced. If they didn't, they pecked the S minus, they did not get reinforced. And the animals quickly learned to discriminate. They had a perfect discrimination ratio of 1.0. And what you do is you take all the correct responses divided by total number of responses. If they make no errors, they only make correct responses. That's going to be 1. If they can't discriminate, it's going to be 0.5 or particularly even less. And that suggests that they're not discriminating at all. So they switched it around. They used a new set of pigeons, importantly. So it wasn't like they were using old pigeons that might have formed a concept bias. These were a brand new set of pigeons. And now the S plus is the absence of something, the key, and the S minus was the dark spot. And the pigeons could not learn this. Rats cannot learn this. Humans cannot learn this. We cannot learn that the absence of something is the S plus and the presence of it is the S minus. It seems to be the way we're wired, and we cannot respond to what's missing. Probably because what's missing is such a large thing. So I'm going to teach you that feature negative, feature positive effect is not Hitler's activity during World War II. The feature negative, feature positive effect has nothing to do, as far as I can tell, with differential calculus. Generally, it doesn't have to do with the hip hop movement. And last time I checked, Donny Osmond was not involved. So what is the feature negative effect? Well, you don't know because I've told you what it's not. If I teach you what is, that's a much more exact method of learning. And so we just don't seem to learn very well by learning all negative exemplars. We have to learn what is. And we'll put all of this together in our discussions. We're going to put together why this peak shift, discrimination, and even teaching verbalizations is so important. And I'm going to give you a couple examples of this feature positive, feature negative effect that I think you'll really enjoy. But I think I've droned on enough, especially since I'm putting this up later than I planned. And enjoy, and I'll talk to you on Thursday.